This is section 6.1, functions and equations in two variables. First question is, why do we need two variables? Well, many times problems in life depend on more than one variable. For example, the area of a rectangle depends on both the length and the width. Your GPA depends on not just the grades in your courses, but the credit hours for each course. And things like heat index can depend on both temperature and humidity. Now, functions in two variables, we treat the arithmetic operations of addition, multiplication, subtraction, division the same, but our function notation expands to account for the two inputs. So instead of just f of x, we have f of x comma y. The difference function of f can be represented symbolically by f of x y equals x minus y, where z is f of x y. In this case, we have independent variables x and y and a dependent variable z. We can evaluate expressions using functions of more than one variable. F of xy equals 3xy squared. So f of 3 comma 2 is simply 3 times 3 times 2 squared, which is 36. I can have a of bh equals 1/2 bh. This is the area of a rectangle. Is base times height. So a of 10 comma 5 is 1/2 times 10 times 5, which is 25. So again, we're just looking at more notation than anything else, so we don't want to get caught up in the notation. Now there is something called literal equations. This is something that's very interesting. It's simply an equation that has more than one variable in it. We've actually been dealing with this before. We saw equations for lines where we had y equals mx plus b. And typically when you're dealing with a literal equation, you're asking to solve for one variable. And you did that a lot as well. You already sat there and had maybe ax plus by equals c, and when you were told to solve for y. In general, when solving for specific variables in literal equations, we simply need to treat the variable we're solving for as the only true variable and treat everything else like a constant. Let's see how this works. The equation for the volume of a rectangular prism is V equals LWH, so volume equals length times width times height. Well, if I want to solve this equation for W, then V equals length times width times height, I really want to treat the W by itself. So I want to get it by itself. So to get it by itself, I have to get rid of the L and H on the left-hand side, and they're being multiplied by the W, so we have to do the opposite. So I'm going to divide both sides by LH. So W equals V divided by LH. Now, we can also take this now and say find W when your volume's 80 meters cubed, your length is 9 meters, and your height is 2 meters. Well, because we've already solved for W, we can just take the now manipulated equation and plug in V, L, and H. We get W equals 80 divided by 9 times 2, which is 4.44 meters. Now again, we could have plugged in originally if we weren't told to solve for W to begin with. We could have plugged into the original equation and then manipulated and gotten W later. Now a linear equation in two variables is any equation that can be written in the form ax plus by equals k. Notice this is just the standard form for a line. Now when we have a pair of equations that are written like that, this is called a system of linear equations because they involve solving more than one linear equation at once. Now please notice a solution to a system of linear equations consists of a single x value, consists of x value and a y value that satisfy both of the equations. In other words, there's a point where the lines intersect at which satisfy both of them. Now the set of all solutions is called the solution set. Now please be aware that you may have one solution if the lines intersect. You may have infinitely many solutions if the two lines are the same and lie on top of each other, or you may have no solutions if the lines are parallel. Here's examples of this. This is an example of the lines intersecting at one point. This red and blue line. Here the red and blue line are on top of each other, so they literally make purple. They intersect everywhere. Here the red and blue line do not intersect anywhere. These two are both called a consistent system of equations. In other words, there's an answer to these two systems. Here there's infinitely many solutions. Here there's one solution. This is called an inconsistent system because there's no solution. These two are both called, this is known as an independent These are known as independent equations. These are known as dependent equations. We don't call these anythings. And another way to think of them is two distinct lines, both lines being the same and the two lines being parallel. In other words, they have the same slope but different y-intercepts. The question is how we actually solve these systems of equations. Well, we're going to learn two methods in this section. The first method is what's called the substitution method. I'm going to give you the steps, then give you examples of it. When you have a substitution method, you're basically going to pick one equation and solve for one of the variables. So you're going to have an equation, and you're going to have an x and a y, and you're either going to solve for the x or solve for the y. General rule of thumb is that look for an equation that has either x or y with a coefficient of 1, because those are the easiest ones to solve for. Once you solve for that variable, you're going to plug what's left. You're going to substitute that into the other equation that you didn't pick, and you're going to solve for the other variable. Now once you solve for that variable, you're down to step 3. You're going to take that variable, plug back into one of the equations in step 2, and solve for the remaining variable. And your answer should come out in the form x comma y. Let's see how this works. I have two equations. This is a system of equations. I know it's a system because there's two or more. I have 2x plus 5y equals 9 and x plus 4y equals 6. I'm going to pick one equation and one variable. Notice this bottom equation has an x coefficient of 1, so I'm going to pick the bottom equation and solve for x. I have x plus 4y equals 6, so x equals 6 minus 4y. That's my first step. My second step now is to substitute. It means I go to the other equation I used, which was the top equation, which was 2x plus 5y equals 9. On my first step, I solve for x. I'm going to pick the x in this next step, and instead of x, I'm going to substitute for x. In the first step, we said x was 6 minus 4y, so instead of x, I'm going to plug in 6 minus 4y. Notice on this step here, I now have an equation with one variable y. We've done this before. We've solved equations with a single variable. Let's distribute the 2. 2 times 6 is 12. 2 times negative 4 is negative 8y. Plus 5y equals 9. You get negative 3y is negative 3, so y is 1. Please do not stop here. A lot of people get here and say, we're done. You're not done. You're only halfway home. These are lines. They intersect at points, and points have two coordinates, x and y. So let's take this one we solved for originally. This x is 6 minus 4y. And let's plug back in for y now. So x is 6 minus 4 times 1. 6 minus 4 is simply 2, so my solution is 2, comma 1. You should be able to take this solution now and plug into both of these equations, and it should work. 2 times 2 is 4, plus 5 times 1 is 5, 4 plus 5 is 9, 2 plus 4 times 1 is 6. That's correct, so this works for both of them. Here, we'll do the same thing. Notice, though, right away that none of your coefficients are 1. I'm going to avoid the one with the fraction because it really doesn't look very friendly. However, I notice on the second one, this coefficient's 2, and all the other numbers here are even. So if I solve for x, I shouldn't have to deal with fractions. So I'm going to pick the bottom equation. I'm going to solve for x again. You get x is 7 minus 2y. I'm going to plug into the top equation now. And instead of x, I put 7 minus 2y. I don't like dealing with fractions, so at this step I multiply everything by 3. The 3 times the 1/3 cancel each other out, so I'm just left with a 7 minus 2y. 3 times 2y is 6y. 3 times 5 is 15. Now I combine like terms. You get 4y is equal to 8, so y is 2. And again, we're going to plug back into one of our original steps. In step 1, x is 7 minus 2y, so x is 7 minus 4, which is 3. So my solution is 3 comma 2, and again we can plug in and verify this works for each of these equations. There's a second method we have, which is called the elimination method. In the elimination method, we want to start by writing our equations in standard form, ax plus by equals c. And it's actually easiest if a, b, and c are not fractions. In fact, that's one of the first steps you want to do, is if you do have fractions, is to get rid of them. Next, what you're going to do is you're going to look at the least common multiples between your x's and the least common multiples between the coefficients of your y's, and pick the easier of the two to deal with. In other words, we'll talk about least common multiple in a second. If you have a least common multiple of 5 and another one least common multiple of 60, you pick the smaller number. We're then going to multiply one equation until one of the coefficients is the least common multiple, and the other is the opposite of the least common multiple. So we want one to be positive and one to be negative. We're going to add the two equations together and solve, and then we're going to solve for the remaining variable. Again, this is kind of confusing, so let's just walk it through. Here are two equations. 2x plus 5y equals 9. X plus 4y equals 6. Here, 2 and 1. The least common multiple between 2 and 1 is the smallest number that's a multiple of each number, which is 2. The least common multiple between 5 and 4 is 20. That's much larger, so let's deal with this one. The least common multiple is 2, which means that this top equation already is 2, right? And I want them to be opposites, so I need the bottom equation to be negative 2. So I'm going to leave the top equation alone. Here's my top equation. I'm just going to shoot it off to the side and not touch it. My bottom equation, this x plus 4y equals 6. I want the coefficient of this x to be negative 2 because I want them to be opposites. So I'm going to multiply this entire equation down here by negative 2. That's where this negative 2 comes from. So negative 2 times x is negative 2x. Negative 2 times 4y is negative 8y. Negative 2 times 6 is negative 12. I'm now going to line these two equations up and add them together. The reason I want them opposite is that when they add together, they cancel each other out. 2x minus 2x is 0x. 5y minus 8y is negative 3y. 9 minus 12 is negative 3. I now have a very simple equation. Negative 3y equals negative 3, so y is 1. I'm now going to take one of my equations, x plus 4 times 1 equals 6, solve for x, and therefore my final answer is 2, 1, which we already saw before in the prior example using our substitution method. Now, why would you use elimination method? I think the elimination method is actually much easier to use when you're dealing with fractions, because we get rid of fractions quickly. Here, I have a fraction in my first equation, so I'm going to multiply the top equation by 3, which is what we did here. Multiply the top equation by 3. 3 times 1/3 x is just x. 3 times 2y is 6y. 3 times 5 is 15. Now, my bottom equation stays the same. I have x plus 6y equals 15. 2x plus 4y equals 14. Least common multiple between the x's is 2. Least common multiple between the y's is 12. So again, let's eliminate the x's. The least common multiple is 2, which means the bottom one already has 2 there. I don't have to do anything with it. I'm just going to bring it over to the side. The top one, I need to make it opposite. So I'm going to multiply the top one by negative 2. That's where this negative 2 comes from. So negative 2 times x is negative 2x. Negative 2 times 6y is negative 12y. And negative 2 times 15 is negative 30. Here are my two equations. I simply add them together. Negative 12y plus 4y is negative 8y. Negative 30 plus 14 is negative 16, so y is 2. Plug back into one of our equations. 2x plus 4 times 2 is 14. X is 3, so again my solution is 3, 2. Notice no matter which technique we use, we wind up with the right equation, the same answers on both. So let's say it's solving systems and linear equations in two variables. What we're going to do is get a single point. Excuse me. Let's look at what happens with our solutions. Okay, we're going to wind up with different situations. Over here we got single points when we got answers. Okay, this told us that when we had single points, it was a consistent system and it was independent. In other words, we had the situation back like we had up here. Consistent system, independent. Okay, two distinct lines. However, if we do our elimination or our substitution methods and we're reduced to a situation where we get 0 equals 0, so in other words, both sides are equal and there's no variables present. This is a consistent system, but it's not dependent. In other words, the two lines are the same, so when you do the elimination method, they're going to cancel each other out. Okay? When you get 0 equals 0, this means you have this situation where the two lines are the same. It's a consistent system, equations are dependent, and there's infinitely many solutions. The last situation you can have is when you eliminate all your variables and reduce the equations down, you get something like this, 9 equals 0. In other words, both sides are not equal. No way 9 can be equal to 0. It never happens. This is a situation where the lines are parallel. This is an inconsistent system. This is this situation. You will not find any solution where these two lines intersect at. Let's look at an example. I have x minus y equals 5 and x minus y equals negative 6. The least common multiple here is 1. Least common multiple here is 1. So I'm going to eliminate the y's. So I'm going to leave this top one alone. I'm going to multiply the bottom one by negative 1. We get negative x plus y is 6. When we line these up, we get x minus y is 5. Negative x plus y is 6. Notice these cancel out. You simply get 0 equals 1. There are no variables left. This tells us we have parallel lines, and hence we have an inconsistent system. Now we have other situations of equations in two variables other than linear equations. Here's an example of, this is actually a circle and this is actually a hyperbola. We can apply our same approach to this. Okay, here we have our x squareds. Our LCM for our x squareds are 2. Our LCM for our y squareds are 3. So we're going to eliminate the x just because they're slightly easier. I'm going to multiply this top equation by negative 2. We get negative 2x squared. Minus 2y squared is negative 8. The bottom stays the same. You get 2x squared minus 3y squared is negative 12. We add these together. The x squareds cancel. You get negative 5y squared is negative 20. So y squared is 4. So y is plus or minus 2. So if you plug back in here to x squared plus y squared equals 4, you're going to get x is 0. So we have simply 2 points, 0, 2, and 0, negative 2. And if we were to graph these, which is not something we're going to sit there and worry about too much in this course with conics, here's the circle, here are the hyperbolas, and this is where they intersect at 0, negative 2, and 0, 2.